Is this on? Okay. Hi, I'm Ryan, and this is work that I did with some colleagues from Rochester Institute of Technology, not to be confused with University of Rochester. Most of the work was done by Matt Lee, but he couldn't come today, so I'm going to talk about what we did. So what is transactional memory? And feel free to interrupt me if you have any questions as I go. How many people here have used STM and Haskell? Okay, everybody knows. All right, great. So transactional memory is merging of two ideas, being able to express atomic pieces of code and an implementation that uses speculation to attempt to run and then detect if there were any problems while it ran and kind of managed it after the fact. Haskell STM adds two additional ideas. The ability to efficiently block a transaction when conditions aren't right for it to continue, and when conditions may be right to attempt it again. And then this compositional aspect where we can take two transactions, which may be blocking, and if one blocks, try the other one. But we have to do this while still holding to those previous two properties. So I'll be focusing on two implementations. But the first is the default one that you get when you use GHC right now, and that's a fine-grained locking implementation that's based on OSTM. And our new work, which is based on TL2. And these are both well-known in the transactional memory community. By the way, this feature of retrying or else, it's not widely used, or it's not widely available in other transactional memory systems. Some of the ones that have their roots in the functional world that have sort of copied what Haskell has have them, but generally it's not available in the research community. So, so part of our challenge was to extend TL2 to support this blocking and retry. So jump to the end. Here's our results. I put the results here because it may be a little bit easier to kind of understand the trade-offs of the implementation if we first kind of see that we get better performance on just sort of micro benchmarks that are running a concurrent data structure, so red, black tree, and skip list. And then this other benchmark that's a little bit strange, but it finds this corner case in really large transactions. And you can see at the bottom, that blue line, the current GHC implementation does very poorly. And our new one kind of tracks the performance of a compare and swap based implementation, which it shouldn't do. That points to deficiencies in the compare and swap implementation. And another really interesting benchmark that we decided to do is to take the par monad and swap out its nice compare and swap based scheduler and put in a STM based scheduler. And the GHC, the current implementation, does pretty well, but then we see it kind of hits some corner cases and falls off in performance as we get more contention. And I'll talk about some specifics of why that happens.
Low is good on that graph.
Yeah, low is good on this graph.
On the previous one, high.
Correct, yeah. It's a little bit hard to, if you do speed up instead, it's hard to kind of really see some of this. So the features that we need to support with our implementations are this atomicity, speculation, retry, and or else. And we can see all of that in this code. So a transaction is where they atomically kind of takes this STM action that is built up and turns it into the transaction. And we have reading of transactional variables, and we have writing to transactional variables. We have an or else composing two different options, and this option here is going to block. So an invariant of this example is if x starts out smaller than y, then it's going to go, and if x kind of catches up with y, then it doesn't increment x, and it'll just kind of start incrementing y at that point. So, so we always have x smaller or, smaller than y. So how are we going to implement this? Well, if we replace tvars with just IOREFs, then when we go here, some of these writes could happen in between the two reads from some other transaction, and that wouldn't be good. So what we're going to do is just delay writing until we've decided that everything went okay and everyone else knows that, that we're going to do the writing. So in the FineGrain locking implementation, this is the existing GHC implementation, we're going to keep this TREC, transactional record, and we're just going to record all of the reads that we do, record the value that we got when we read it, and just store that in this chunked linked list. And the tvars themselves will have the value, and then they'll have this watch list, which will be things that need to be woken up if we change that particular tvar. And then we have this version number, which helps us in the commit. So each value is going to double as a lock and the value. So these point to heap objects, and if the value points to a transactional record, then that tvar is locked. If it points to some other heap object, then it's not locked. So we can see when we perform a read, we're going to add an entry. When we perform a write, we're just going to fill in the new value inside that transactional record, and we're not actually going to update the transactional variable. Then at the very end, when we get to committing, we're going to check and see, do all the values in the transactional record match, and can I get the locks for all of the places I want to write? And it's a complicated kind of protocol for that, but once all the locks are held, then it can go ahead and perform all the updates and bump this version number, and everything's happy. Yeah, the version in the chunk is it's a detail. It's basically so that we don't have to allocate a structure later for it, but it's when we go through the first time and we're checking to see, do the version numbers, do the values match that we read, we store the version number that we see. And then we check that all again after we've acquired all the locks, and we compare the version numbers this time too. And if the version numbers change, that means while we were in the process of getting the locks, somebody else committed, and we detect a conflict. So what the property that gives us is we never have to take locks on things that we read, which is a really nice property. Read-only transactions never get in each other's way. So our new implementation takes a very different approach. Instead of storing the values, we're going to just use that sort of version number idea. And our read and write set are not in one transactional record, but are split. So when we read something, we first check to see, does the value exist in the write set? Have we already updated so that we see our own writes? And if we don't find that value, then we just add that as an entry in the read set. when we go to write, we just add a value into the write set. We don't even really bother with much else. But we do always check to see if the transaction's locked. And here the lock is in the same spot as this version number. So odd versions are locked, and even versions are a version number. And we also store the thread ID in the odd version too. So if we encounter, when we're reading, a locked transactional variable, we wait for it to be unlocked and go through this process of trying to see if that locked variable was going to affect anything. And this is called timestamp extension, and it's in one of the papers. So the other thing that we have is this global version number. And when we actually go to commit, well, let me back up a second. If we didn't have the global version number, every time that we did a read, we would need to check and see if all of our read set is valid. And the reason for that is we want this property called opacity in TL2. And that means that we don't want to be able to execute after something has gone wrong. So if we go back to our example here, if in between this read and this read, somebody else does a write, in the original GHC implementation, there was nothing in there that looked for any changes in this other read variable. We just look it up, and it's not in the transactional record, and add the new one. It's not till the end that we validate that all of our reads are the same. But with TL2, we're going to always validate our reads. And if you think of that, that means every time you do a read, you're going to read all of the, update all the previous kind of version numbers and go check through. And that gives you this n squared number of times you have to visit the tvars as your kind of computation goes on. So the global version number is what's going to aid us there. So instead of doing this validation every time we read, we're going to look at the global version, and if it hasn't changed, then nobody else could have updated any other transaction, any other variables, so we can just kind of keep going. The problem is that means everybody is constantly looking at that global version number, and if anyone increments it, that slows everyone down. So we have a global bottleneck, but we gain this property of opacity. So summarize the properties that we have. The original STM has no global bottleneck, but it has this lazy validation, which could be bad, it could be good. And TL2 has a global bottleneck, which is bad, but it's kind of a small one. And we gain the property of opacity.
Why is that good?
Why is opacity good?
Yeah.
That's a good question. The benefit is we don't have to worry about running what are called doomed transactions. So with lazy validation, we can run after seeing an inconsistent view of memory.
Why is that bad?
That can be bad because it leads to unexpected bugs, like this one. So I just submitted this a few days ago, yeah. So what happens is, you remember that idea of having some invariant that holds. I can write code as a user that expects that invariant to hold. And in fact, that's the whole reason why I'm using STM, is I want that to hold. And I don't want to think about it too much. But it turns out, right now, I do have to think about it. If I do something that has a large memory effect, we don't handle it correctly right now. It's not that it can't be handled correctly, but it's hard to think about all the possible ways in which things can go wrong. In the context of hardware transactional memory, there's a really strange thing that can go wrong that's really unfortunate. It seems like most things that could go wrong, well, you execute along and then things fail and the hardware takes care of it and cleans up. But there's one really strange thing that can go wrong, which is you accidentally jump to the commit transaction instruction, and then it commits the transaction after seeing all of this bad state. So the original paper says the thing you have to watch out for are infinite loops. And you still have that problem if you have a non-allocating infinite loop. And again, this is implementation detail. So if you want STM code that's correct, you really need to build everything with the no omit yield, and that may have a performance hit. There's other memory effects too that are just sort of unfortunate. Say you have a infinite tree implementation of something, or like a memoized Fibonacci. And you know, as an invariant, you only look up values that are less than 10 out of that Fibonacci table. But you execute some strange code, and all of a sudden you look up the value 1,000. And it allocates a lot of memory, memoizes a lot of Fibonacci numbers, and you never get that memory back. It's a big memory leak. So that's sort of inherent to this lazy validation. So here's the opacity problem. In particular here, GHC handles large allocations in a unfortunate way. We get to a point in execution where we can't really do anything, and we can't back up, we can't start GC, and so we sort of panic and ask the operating system for more memory, and when it's huge, when we ask for a huge amount of memory, then the operating system just kills us off. So even though it's not a code path that should be able to happen because of our invariant, it does. So TL2 avoids that problem. Not quite ready for that slide. So let's look again at our examples here. Why does the FineGrain perform poorly on this? This is simply doing a long transaction down a really, really long linked list, and then performing a little change at the end of the linked list. So we have a huge read set. And in the TL2 case, our read set just keeps growing, but we don't really revisit it. We only revisit it occasionally when another transaction successfully does something at the end of the linked list. But in the GHC FineGrain one, every time we put a new, read a new TVAR, we have to see, is this a TVAR that we've seen before? And so we have to search through the entire set. Really, all that we care about is seeing whether this is a TVAR we've written to before. But the two things are in one transactional record. So we pay that n squared cost to traverse down the linked list. And in this one, we're sort of trying to distribute tasks with a double-ended queue. This is work stealing, and our scheduler just implements this double-ended queue concurrently. And when we get enough threads here, which this is surprisingly stable. It hits this point and just kind of explodes. You can see where the top of this line is matches with single-threaded performance, which indicates that only one thread is doing work. And what ends up happening is one thread can pull things off of the queue faster than anyone else can get to any work. And so it starves all the other threads. And with TL2, we don't end up getting that starvation behavior because there's less overhead with the system. So, conclusion here, there's still work to be done. We need to explore fixing the problem with memory effects and the regular STM. We need to try and take the good parts of our TL2 implementation and bring them into the FineGrain implementation, like having a split list with write set and read set, and that should fix a lot of the problems. And we want to explore the TL2 with some other work that we've done on improving the amount of memory that transactions have to touch and exploring hardware transactions. So that's it.
So you said next step is to sort of bring the good parts of TL2 into our FineGrain implementation. What are the bad parts, and why wouldn't we just want to?
Yeah, the bad parts are the global bottleneck, which at some point, some number of threads, that's going to be the dominant performance factor. Because, right. and the reason is, it's trying to get this sort of global information. Has any other transaction committed? But that's an expensive question to ask. If you really have independent tasks, you shouldn't have to ask somebody else if you're done. And so at some number of threads, it's just not going to perform well.
But so you can't.
It's going to stop scaling.
But you can push this off, this point off, sort of arbitrarily by sort of sharding that global counter, can't you? Or?
Yeah, so there's been a lot of work on doing things like that. So you do things like you look at the memory addresses of all of the TVARs that you touch, and you know that they fall within this range of memory addresses, and somebody else's falls in another range, and you have a different sort of hierarchical global lock for those.
Yeah.
So yeah, there's other work. TL2 is a pretty conservative one, but it's an easy one to implement and to compare and get this opacity property. The other ones have other sort of issues of how do I handle retrying or else, which, by the way, I missed that. There's a really nice thing about retrying or else with TL2. Because I just keep the write set as this long thing of linked lists, when I hit the or else frame after I kind of hit the retry and I go to see if I should jump to the other one, I don't have to merge these transactional records. I just set the write set pointer down further in the linked list. So I can throw away writes by just kind of moving where in that list I am.
Hello, Matthias here. I'm wondering if there's certain spaces where you could exploit that we can make one kind of error, and that's not too much of a problem. Basically, false positive, but not false negative. What I mean, for example, is for the opacity, we could sometimes go on with a doomed transaction as long as we never abort a transaction that's not doomed. And if most of the time we catch doomed transactions, it's fine. If we sometimes do them, then we're not worse than the original implementation, but most of the time we catch them. That's one thing. And another thing that I thought of is for your global version check, instead of having one global version number, you could have a vector of those, and they all individually have logs. And then basically whenever you have a variable you read, you hash to a location, and the set that you check is basically a union of all of those. And then you can even do play all the games that we do with Bloom filters and stuff like that. Yeah. I wonder if that makes any sense. It's basically just stealing the ideas that people have for the like concurrency in the large for in this case.
Yeah, there are over like I can't remember what we're up to. Something like 400 papers on transactional memory. A lot of this has been explored very much. There's only 3 papers on Haskell transactional memory. So we have a lot to catch up with. But yeah, there are a lot of very interesting and good ways to avoid that global bottleneck. But at the same time, as you start to add more and more things, you just end up doing more. And the best strategy for transactions is they don't conflict, make them as minimal as possible, and just let them get out of the way.
Yeah, especially if you have on only one machine, and for currently sized computers, a single, like a vector that only has a single element might actually be the optimal strategy.
Yep.
Thanks.
I think we can take one more quick question. Simon?
Okay, so
Yeah, there are a number of different threads going on here. Like, so you talked about this memory effect thing. That's one kind of thing. Another kind of thing is robustness, right? You showed that there were sort of bad performance spikes. And a different kind of thing is this sort of n-squared-y kind of performance. So there's a number of different things going on here. And I'm not quite sure what. It's hard to tease them apart. Like some of the existing implementation, if you separated the read sets and write sets, does that deal with robustness?
Yeah.
Because you said that's the quadratic thing, or
yeah, that's why there's a lot of things on that future work slide, and it's not future work merge.
I see. So at the moment you're not saying I've got the solution. You're more saying I've demonstrated that that we can do better.
Yeah. In certain cases.
Yeah. All right.
And the other sort of direction is I stress this on concurrent data structures. I've never seen anyone who uses a concurrent data structure that ends up huge, the size that I have, and really runs that workload. Real-world applications have a couple of queues that they kind of merge together. And in that case, the very simplest implementation where the transactional record is tiny, you don't get an n-squared effect because you have 2. So it's hard to say if 90% of the uses are not going to benefit, then is it really worth it?
Let's thank our Ryan again. And now we have Remy Wang to talk about Autobahn.